Hi YouTube! So let's write another Linux kernel module. This time we will access this BMP280 pressure and temperature sensor over SPI. And you may wonder, because last time I've accessed it over I2C, but this sensor supports both SPI and I2C. So this time, instead of connecting it to the SPI pins here, or to the I2C pins here, I've connected it to the SPI 0 pins here to communicate with it. So let's write a Linux kernel module to access it. So here I'm connected over SSH to my Raspberry Pi, and inside my Linux driver tutorials folder you can see all the various Linux drivers I have already written. And of course, like all the other ones, I will share my source code over GitHub with you, so if you have a project and you want to use them, you're free to do it. And here, our first Linux kernel module was just a simple hello world kernel module, which will print out 2 lines to the kernel log, and I will use it as a base for today's video. So let me just copy it and create a new folder called 10 SPI BMP280, and I will change into this folder. So inside here we have file module.c with the source code for a simple hello world Linux kernel module, and we have a makefile. Let me just rename my module to SPI BMP280.c, and of course I have to change it in the makefile as well. Instead of building the object file mymodule.o, I want to build the object file SPI BMP280.o. 200, not 180.o. Okay. And I will open it up. And here we have just the standard code for a simple hello world Linux kernel module. And now I will modify it to read and write some of the BMP280's register. But before I start, I want to make 2 things clear. Last time I really read out the current temperature. This time I will just read and write 1 or 2 registers to show you how it works, and the rest is easy, just like I've done in my I2C video with this sensor. And the second thing, I won't discuss how SPI works in this video. Maybe I will make a video about it later, but if not, there are a lot of videos on YouTube available which will explain to you how SPI works. Okay, so now I will just add a new include here. We need the include linux/spi/spi.h to get some functions to access the SPI bus. And I will change the description here as well to a simple Linux kernel module to read and write some registers of BMP280 sensor. Okay, and now the first thing I have to do is I have to add a define and a variable here. So to define my bus number is the number of the SPI bus I want to use, and I've already shown you I've connected my sensor to SPI 0, so the bus number is 0 here. And the second thing we need is a global struct variable here from the type SPI device, and I will call it BMP280/10. Okay, and here and this function here is called when the module is loaded into the kernel, and here I have to initialize my device and I have to set up the SPI bus to access it. So the first thing I will do is I will declare a variable from the type struct SPI master, and This variable contains all the information about the physical SPI bus. We have to set up the SPI bus with some parameters to make read and write accesses to this device here. Second thing I will need here, I will define a struct from the type SPI board info, and I will call it SPI device info. And this is just a struct containing all the parameters identifying my SPI device. SPI device and the parameters, I mean following one. Here I can set a name and I would choose BMP280 here. I can set the maximum speed, bus speed in Hertz, and I will choose 1 megahertz here. The next thing is the number of the SPI bus I want to access, and this is of course my bus num. Okay, another parameter is the chip select we want to use. As you may have noticed, for the SPI device 0 there are 2 chip selects available. I will use chip select 0, so I'm typing here, I'm setting it here to 0. And the next one is the SPI mode. I will just set it to 3, which is the default SPI mode. But as I already have mentioned, I want to go too much into the details about SPI here. Okay, and now we need to get access to our physical SPI bus. And we can do it by calling the method SPI bus num to master, and this will return us a pointer to our physical SPI bus. And as a parameter, it needs the bus number, which is in our case 0, or the number after we define my bus number. And now we have to check if we could get the master, because if there isn't a SPI bus 0 on the device, it will return us a null pointer. And if it returns a null pointer, we can't go on. There is no SPI bus with number, my bus number, and I will return -1 to indicate there is a fail. Okay, so the next step is to create a device, a SPI device. And we can do this by calling the function SPI new device. New device, and as an argument we need to pass as a pointer to our SPI bus, which is master here, and we have to pass this variable with all the information about our device. Okay, and here it is just the same. I will add a comment here, create new SPI device. Of course, here it's just the same. If the function returns a 0 pointer, it couldn't create the device. And I will return -1 here. Okay. And if this works, we will set another parameter for the device, bits per word, and this parameter means how many bits will be written or read if one access to the SPI bus is made. In our case, we just want to read 8 bytes per access. So the next step is to set up the bus for devices parameters. And we can do this by calling the function SPI setup, and we have to pass our device here. And what this function does is, if you, for example, let's imagine the bus, before we call our kernel module, the bus speed is set to 2 MHz, but our device can only operate with 1 MHz. So we have to change the bus the frequency the bus is running, and we do all of this by using the function SPI setup. And in case this doesn't work, I will print out could not change bus setup, and I will unregister our device. So, and I will return -1 here. Okay, and after we have come so far, everything is set up, initialized, so now we can read from the device. So here I have the datasheet of the BMP280 temperature sensor, and at first let's look how we can read and write to it over SPI. So here we have a chapter about the SPI interface, and if I scroll down a little bit here we have the things we have to write, so the things we have to send to read and write from our device. So as you can see here, we have to set chip select to 0, it's low active here, and then we have to, for a write, we have to write the address out we want to write, and the most significant bit on this operation has to be 0, and then we can write out the data we want to write. And then we have to set the next address and the data we want to write. And if we want to read from the device, the difference here is we have to, the most significant bit of the address has to be 1, and then there comes the device address, and then there come so many a lot of bytes, all the data we want to read from, and you will read from the device until chip select will be set again to 1. So that's how to read from the device. And now let's take a look at what register we can pick for reading and writing. So a good choice here is the chip ID register, because it will always contain the value 58 hexadecimal. And for trying a write, I will choose the config register. Yeah, I could pick any other register, but I will go with the config register. So let's start by reading the chip ID. For this, just let me declare a variable up here, ID, I will call it ID, and here read chip ID. So to read something, so we have to write the address out first, and then we can read the data back or the value back. And for doing this, I will use the function write 8-bit, read 8-bit. As an argument, I need to give the SPI device we want to read from, and the second parameter is the thing I want to write, I want to read from, and this is of course the address D0 here, and because we want to read from it, the most significant bit must be 1, and this is true for D0. Okay, and now let's print it out so we can see if it worked fine. ID. Okay, and the last thing I want to do here is I want to try a write. Write to config rec. So for writing, I can use the function SPI write, and it needs the following arguments. The first one is the device we want to write to, which is BMP280 def. Then I have to pass the things I want to write, and I have to pass the size in bytes of the things that should be written to it. Okay, and for this purpose I will use a second variable, u8 var. Okay, so the first thing has to be the address we want to write to, and the most significant bit has to be 0. So in this case I will type 75 here, because if I set the most significant bit to 0 here, it will become 75. And the second value is the value we want to write, which is 40 in this example. So here I have to add val, our values we want to write, and the size of it in bytes, which will be 2 in this case. And to check it, I will just read it back here, and of course I have to change the address to F5 here in this case. And instead of chip ID here, I get the config rec value. Okay, and now there's only one thing left we have to do. If we unload our kernel module, or if we remove our module from the kernel, we want to destroy or remove our SPI device too. So if BMP280 device, if this is not null, I will just unregister the device. Okay, so I will try to compile it here, but I'm pretty sure I've made a mistake or two. Yeah, okay. If BMP device, okay. Okay, but not here. If BMP device. So let's build it again. Just warnings. Oh, yeah, okay, I have to change it here. I want to have an array here. So yeah, an array with 2 elements. Big mistake. But now it should compile without warnings. Okay, and now I will try to load my module into the kernel. But I will get an error here. Oh my god, what's wrong? What happened? So to resolve it, I will take a look at our kernel's log. So we get the warning, could not create device. Okay, couldn't create our device. And it says chip select 0 is already in use. And this error is specific for our Raspberry Pi, because if we look to all the device files here, and if we search for SPI, we see there are already 2 device files for SPI, and the Linux kernel module standing behind this device file is already using the chip select 0, so we can't use it for our kernel module. So we have to remove the Linux kernel module, which is responsible for this device file here. And the second important thing, you have to get this running, you have to enable SPI. You can do it with sudo raspi config and then just enable SPI. So the kernel module to access the hardware registers of the SPI is enabled. But how can we remove this kernel module here? And I didn't know it too, so I searched for it on the internet, and here in this Raspberry Pi forum I found this post here with just the same thing we have seen in our kernel module. And he found a solution how to fix it. We have to create a file with a device tree overlay, and this will remove the Linux kernel module who's responsible or who's already using chip select 0. So what I have done is I just copied this thing here on my Raspberry Pi, and we have to compile the overlay and then we have to load it. So let's do it. So as I have already said, I've just copied it into my home directory, and now I will copy it from the home directory into this directory here. I will compile it with this command here. Okay, and now I will load it. And now if we look again at our device folder and read for SPI, yeah, we only have this module running here. So now we should be able to load our custom kernel module. Yeah, we have successfully loaded it. Sorry, okay, and now let's check the kernel's log. DMS tail. So here we see the chip ID, which was read back, is 58. Let's check it. Yeah, that's true. And we could successfully write our value 14, because the reset value of the config register is 0. So we were able to read from SPI device and write to SPI device by using a Linux kernel module. That's it for today. I hope you've enjoyed the video, and I will see you in the next one.